In today's video, we're going to discuss a topic completely glossed over in introductory physics classes, but it's an extremely valuable problem-solving tool for all branches of science, from the mundane to the most cutting edge. And by using this technique effectively, you'll be able to build your physics intuition, understand concepts more clearly, contextualize bigger picture ideas, and become more competent in your test-taking abilities. By the end of this video, you'll be able to solve this problem without any hesitation. That's right, one equation with three unknowns. Sounds hard? After watching, not nearly hard enough. Today, we're going to do dimensional analysis. Let's get started. Hi everyone, this is John, and welcome to my channel, drjohn.dev. I have a PhD in physics and have been helping students solve physics problems just like these for over 15 years. For personal help and appointments, visit my website at drjohn.dev. Make sure to subscribe to my channel and hit that like button. Before getting into the weeds of how dimensional analysis is used in physics, it's important to know a little bit about where it came from and why it's needed in the first place. In science and engineering, mathematics is applied to real physical quantities. And to account for each physical quantity's size and type, the numerical values associated with these quantities must be labeled by a unit. A unit specifies a particular physical quantity and belongs to a measurement system. Quantities with the same units can be compared, combined, and manipulated numerically. For instance, the height of the Empire State Building is 1,454 feet in the English system of measurements, or 443 meters in the metric system of measurements. Although both feet and meters measure the same physical quantity of length, they belong to separate measurement systems and are thus different units. You can see the presence of multiple measurement systems, each with their own set of unique units, can make things complicated to say the least. To circumvent these problems, and to curb the growing proliferation of measurement systems around the world, the International Treaty of the Meter was held on May 20th, 1875 in Paris, France. This meter convention laid the foundation for establishing a world standard for reporting scientific values, constants, and research. The measurement system of choice drew heavily from the metric system, and eventually formed the basis for what's today known as the International System of Units, or SI for short. The SI consists of 7 fundamental quantities, and each quantity is associated with a fundamental base unit. The 7 fundamental base quantities and units are 1. Time, symbolized with an italic T. The associated base unit is the second, abbreviated by an S. Note, the square brackets around any physical quantity denote the unit associated with that quantity. This is a common convention and will be used throughout this video. Number 2, length, often symbolized with an italic XYZ in a Cartesian coordinate system. The associated base unit is the meter, abbreviated with an M. Number 3 is mass, and is symbolized with an italic M. Make sure not to mix this symbol with the meter base unit. The SI base unit for mass is the kilogram, abbreviated kg. This is the only SI base unit that comes with a prefix, which is, in this case, kilo for 1,000. We'll cover more about prefixes later, but just know that for mass, the established SI base unit is the kilogram, not the gram. These 3 fundamental base units are often the only base units you should cover in a first semester physics class. But here are the remaining 4 covered in a second semester physics class, chemistry, and/or thermodynamics class. They are current, symbolized by an italic capital I with its corresponding base unit of an ampere, temperature, symbolized by an italic capital T with its corresponding base unit being a Kelvin, the amount of a substance, symbolized by an N. This is often first encountered in general chemistry course and has the SI unit of the mole. And finally, the luminous intensity, symbolized with a capital I sub V, and having the SI unit of the candela. The SI system does not stop with these 7 base units. These base units can be combined in various multiplicative factors to form 22 derived units with special names and symbols. An example helps highlight this point. Consider Newton's second law, where the net force acting on an object is equal to the product of the object's mass m and acceleration a. For this equation to be true, the units on both sides of the equation must be equal. So the units of force must be equal to the units on the right-hand side of the equation. We can find that. Square brackets follow the normal distributive property of multiplication and can be applied to m and a individually. We know that the base unit for mass is the kilogram, and the base unit for acceleration is meters per second squared. Since this product cannot be reduced further, we know that the base units of force then are the kilogram meter per second squared. Forces are common quantities in physics, and the base unit of kilogram meter per second squared doesn't exactly roll off the tongue. So physicists have made a new unit called the Newton, which is equivalent to a kilogram meter per second squared. A Newton is an example of an SI derived unit. The other 21 derived units can also be formed through their foundational equations. While it's not important to remember all of these relationships, and there's a lot of them, it's important to understand each derived unit really represents a combination of constituent base units. And given the appropriate equation, you could decompose each one. These 7 base units are scaled in such a way that we can see or interpret each unit in a meaningful way, that is, on human-sized scales. For example, we can easily count 1 second and internalize this unit of time. We can also imagine 1 kilogram, just over 2 pounds, as being the mass of, say, a pineapple or a liter of water. What about something a little bigger, like 50 meters? Or how fast is 2 meters per second? In the proper context, we can easily visualize and get a sense for these numbers. Imagine this scenario. This is an Olympic-sized swimming pool. The standard size of an Olympic pool is 50 meters. So here's a concrete example of 50 meters. Now imagine a swimmer. Let's call him Jeff. Okay, not what I was imagining, but let's just go with it. Jeff is going to try and break the world record for the 50-meter free. So Jeff dives in the water and swims the length of the pool in 25 seconds. How did he do? Well, by dividing the distance over time, this brings his average speed to 2 meters per second, which is pretty good for a swimmer. We can easily look up the world record for the 50 meters freestyle swim, which was set in 2009, by the way, by Cesar Cielo at a time of 20.91 seconds, which brings his average speed to 2.39 meters per second. So better luck next time, Jeff. But see how easy the base units are to visualize? Unfortunately, most of the known universe does not operate on human-sized scales. On much larger or smaller scales, these units get much more difficult to internalize. For example, if I ask you how long it would take a pulse of light to travel the same distance of a 50-meter swimming pool, would you intuitively know that or even have a ballpark estimate? Light travels at a constant speed of 2.99 times 10 to the 8 meters per second. Dividing the distance by the speed, we can determine a pulse of light takes 1.7 times 10 to the minus 7 seconds to travel from one end of the pool to the other. It's very quick, but how quick is that? We could easily flip the script in the other extreme. Let's consider the time it takes Jeff to swim the distance of the pool, which was 25 seconds, if you remember. How far can a pulse of light travel in that same amount of time? Well, just multiplying the speed of light by 25 seconds, we can find that light pulse travels 7.5 times 10 to the 9 meters. This is a huge number. Just like the very small number, it's really hard to wrap your head around. To break things down, it's useful to draw comparisons to quantities that you're familiar with. This helps with both your physical intuition as well as your deeper understanding. Let's consider the light pulse again that travels 7.5 times 10 to the 9 meters in 25 seconds. Writing it another way, this distance is 7.5 billion meters. This is such an astronomically huge distance that it makes sense to just compare it to astronomical distances. Let's zoom out for a second and consider some of Earth's nearest neighbors, like the Moon and Mars. In 25 seconds, would this light pulse make it all the way to the Moon? Or would it make it to a nearby planet such as Mars? Or even further than this. A quick Google search reveals that the Moon is 3.84 times 10 to the 8 meters, or 384 million meters away. Whereas Mars is a whopping 2.44 times 10 to the 11 meters, which is equivalent to 244 billion meters away from Earth. So where does that place our light pulse? somewhere in between the Moon and Mars. While these are still difficult distances to comprehend, we are at least familiar with these local objects, and we know that this distance is large, but it's still not as far as somewhere outside, say, our solar system. It's not even as close as one of our closest planets, such as Mars. One technique for making large and small numbers easier to grasp is by wrapping up a quantity's power of 10 in a prefix. I'll show you what I mean by looking at a number line. If you had to place the SI base units on a number line, where would you put them? We can take the word unit for its literal definition as a quantity being equal to 1, or equivalently 10 to the power of 0. This can apply to all SI base units except the kilogram, which already has a prefix associated with it. As the value of a quantity grows, so does its number of digits, and hence its associated power of 10. But instead of using a power of 10, we can use a representative prefix. This is done by simply adding a prefix in front of the base unit and then dividing out the associated power of 10. For example, instead of saying 5,000 meters, I can attach the prefix kilo in front of the meter and then divide 5,000 by 10 to the 3. This forms the kilometer, or kilometer in common vernacular. So 5,000 meters is then the same as 5 kilometers. We can also do this in symbols by simply adding the letter K in front of the M to arrive at 5 km. As a side note, this is where the K comes from when referring to the 5K race. These prefixes are not just restricted to large numbers. For numbers less than 1, there are a separate set of prefixes. So in the opposite direction now, 1,000th of a meter, which is 10 to the minus 3 meters, can be written as millimeter. Although there are prefixes ascribed to almost every possible power of 10 imaginable,
Generate the 1.21 gigawatts of electricity. 1.21 gigawatts!
You don't need to memorize all of them. In fact, from personal experience, I've found only around 8 prefixes to be the most used in physics and science courses. They've been highlighted here for you. For some context, in dealing with measurements of length and mass, the most common prefixes used are kilo, centi, and milli. And in dealing with light, the prefixes tera, giga, and mega are most often used in describing frequency, while micro and nano prefixes are often most used for describing light's wavelength. And as a final note, when dealing with units of time greater than 60 seconds, it's more common to use the conventions of minutes, hours, days, and years. You'd be really hard-pressed to find someone seriously talking about a 3.6 kilosecond rather than simply an hour. But for values of time less than 1 second, the negative base 10 prefixes are still used, such as the millisecond. In real scenarios and problems, you are often not provided quantities in nice, straightforward base units. For these scenarios, you must be able to systematically convert between units. Given light's speed of 6.7 times 10 to the 8 mph, or miles per hour, find how long it takes light to traverse the 50-meter pool above water. So first, how are speed, time, and distance related? By definition, speed is equal to distance divided by time. To find how long it takes the light pulse, we need to rearrange the equation as time equals distance divided by speed. But when we substitute our given values of distance and speed, we see there's a problem. The numerator is in units of meters, while the denominator is in units of miles per hour. Remember, the units must be in the same numbering system in order to combine quantities. We can convert either one, so let's convert meters into miles. The first step is to look up the conversion between each quantity. In this case, we found that 1 mile is equal to 1,609 meters. Now notice, if I divide both sides by 1,609 meters, the left side of the equation completely cancels and becomes a unitless 1. And the right-hand side of the equation becomes a ratio, with miles in the numerator and meters in the denominator. Keeping that in mind, and backing up again to the original expression, notice we could have also just as easily divided both sides by 1 mile. This would have made the right-hand side of the equation equal to 1, and the left-hand side of the equation equal to another ratio, this time with meters in the numerator and miles in the denominator. This is the key behind dimensional analysis. Why? Because you can multiply 1 to any quantity and it remains unchanged. So multiplying our original problem by the appropriate ratio will in effect be multiplying by 1. But which ratio should we choose? Remember, we want to convert the meters to miles. So we want to choose the ratio that will cancel the meter unit and replace it with a miles unit. The second ratio of 1 mile over 1,609 meters effectively does this, so we can multiply our original expression by this one. And after substituting this in and simplifying the fractions, we see the only unit that remains is the time unit of hour in the numerator. This is exactly what we were wanting to find in the first place. Time. So we know we were on the right track and we can be confident about our answer. And now you could actually stop here and you wouldn't be wrong, but how informative is this answer really? Light taking 4.6 times 10 to the minus 11 hours to travel 50 meters? We know it's a really short time, but how short is short? Also, the SI base unit for time is in seconds. So let's try to add a little more context to this. First, let's convert the hours to seconds. We can apply the same logic as before. First, write out expressions relating hours to minutes and then minutes to seconds. Then, looking at the quantity to convert, multiply by a ratio that will cancel the unit and replace it with a new one. In this case, if we multiply by the ratio of 60 minutes over 1 hour, the hours will cancel and be replaced with minutes. But we want seconds, so we can multiply by another second ratio, and this time it's the seconds over minute ratio in order to cancel the minutes and replace it with seconds. Next, multiply all the numbers in the numerator together and all the numbers in the denominators together. And then finally, divide the numerator by the denominator to arrive at your final answer, which we find to be 1.7 times 10 to the minus 7 seconds. This number is at least in base units now, but we can use a prefix to help with the 10 to the minus 7 order of magnitude. We can use the 10 to the minus 6 prefix for micro, which is symbolized by the Greek letter mu, to convert seconds to microseconds. We do this again in the same manner. We know 1 second is equal to 10 to the 6 microseconds, so we can multiply our answer above by the ratio of 10 to the 6 microseconds over 1 second. This will effectively cancel the seconds and replace it with microseconds. After doing the math, this computes to 1.7 times 10 to the minus 1 microseconds. We can also get rid of the dangling 10 to the minus 1 into the 1.7. So our final answer becomes 0.17 microseconds. 0.17 microseconds is a whole lot more concise and, by most standards, prettier than 4.6 times 10 to the minus 11 hours. And overall, it's easier to think about and compare with other known quantities. For instance, 0.17 microseconds is longer than the pause between network packets sent via gigabit Ethernet connection, which clocks in at around 0.096 microseconds. And then on the other end, 0.17 microseconds is shorter than the fastest known protein folding reactions, which occur around 1 microsecond. So this example illustrates an interesting point, which is typically physical processes involving light interactions occur on much faster timescales than most all biological processes. This is part of the reason it's hard to visualize these extreme units in the first place. Moving on. In addition to converting units, you can use dimensional analysis to determine or verify the constants used throughout physics. In physics, you'll encounter many proportionality constants. And while these constants may be given to you in formula sheets, it's often useful to know how constants acquire their units in the very first place. Often, problem sets or exams will intentionally provide variables and mismatched units from their proportionality constants. You have to be aware of this and don't fall for this easy pitfall. Let's see it in action with Newton's law of universal gravitation. Newton's law of universal gravitation states that all objects in the universe share an attractive force proportional to the product of their respective masses and inversely proportional to the square of the distance of separation between their centers. What are the units of this proportionality constant? So there's a lot to unpack here, but let's first translate the words into a diagram, then form an equation, and then apply dimensional analysis to determine this constant. Let's consider two masses labeled m1 and m2. And their distance of separation is equal to, let's say, r. According to Newton's law of universal gravitation, m1 has an attractive force acting on it from m2, and then m2 in turn has an attractive force acting on it from m1. Both of these forces are equal in magnitude since they involve the same masses separated by the same distance. So let's just consider one of these forces and label it F sub g. So according to Newton, F sub g is proportional to m1 times m2 divided by r squared. To form an inequality, we need to insert a proportionality constant. For Newton's law of gravitation, this proportionality constant is usually denoted with a capital G for gravity. But what are the units of G? Is it unitless? We can determine this by solving the equation for G and analyzing each variable's base units on the right-hand side of the equation. We know from before that force has a derived unit of the Newton, which in base units is equal to kilogram meters per second squared. And then each mass carries a unit of the kilogram, and the separation distance, r, carries a unit of the meter. So we can substitute these into the equation for G and simplify. Since we've run out of space here, let's clean up the board and then continue. Now, we can clean up this mixed fraction, and we arrive at kilogram meters cubed divided by kilograms squared seconds squared. The kilogram factors cancel to leave a factor of kilogram in the denominator, which leaves the irreducible base unit form for G as meters cubed divided by kilogram seconds squared. And we can box this answer. Before we go over the challenge problem that I mentioned at the beginning of this video, we're going to cover one last dimensional analysis problem that is quite possible to show up on a multiple choice standardized exam. On these types of exams, dimensional analysis can be a quick lifesaver, as you can eliminate choices without needing to know any of the fundamental physics. Simply apply dimensional analysis and you'll instantly improve your odds of answering correctly. Let's take a look. This problem states a pendulum's period of oscillation is the time it takes a pendulum to make one complete swing from one side to the other and back again to the original side. Which of the following expressions is equal to the period of a pendulum? Is it A, 2 pi times the square root of G over L, B, pi times the square root of 1 over the product of G, L, and M, C, 2 pi times the square root of L over G, or D, pi times the square root of the product of G, L, and M? The key to answering this question is in the first sentence. A pendulum's period of oscillation is the time. So the answer then must also have units of time. We can quickly unit check each answer and eliminate all the answers that don't have units of a second. For answer A, we can distribute the square brackets around each factor, and also note that pure numbers such as 2 pi are unitless, so they can be ignored when doing any type of unit analysis. It's also a good practice to distribute the brackets inside any square root signs or powers. These math operations can be applied to the units after they're already substituted into the equation. Substituting meters per second squared for G and meters in for L, we find that the expression in A has units of 1 over second, which is not the same as the second, so we can eliminate A. Applying the same logic to B, we can substitute in the units for G, L, and M to arrive at second inverse meter kilograms to the minus 1/2 power. We can eliminate this answer as well. Now in C, notice how this expression is the same as the expression in A, except G and L have been flipped. Since these were the only variables contributing to the units in A, we can save ourselves some time by rewriting this as the inverse power of the square root of G over L. Then substitute the units we found in A, and then we arrive at seconds. This is exactly the unit we were looking for. So is it time to box the answer and move on? Well, not quite. Although having the right units is a necessary condition, they are by no means a guarantee of the right answer. So we should at least check the units of D, and only if D is not in units of seconds can we be sure C is the correct choice. Let's keep it in mind though. But if you haven't already noticed, in choice D, the expression is simply the inverse of the square root in choice B. So we can deduce the units here as the meter kilogram to the 1/2 inverse second. So basically we can eliminate D as well. And that leaves us with choice C as the only answer to take units of the second. We know we have the right answer, and we didn't even need to know the underlying physics. Although it's nice to have a multiple choice to be entirely doable through unit analysis alone, often there are at least 2 answers having the same units in a multiple choice problem. But even eliminating half of the options using dimensional analysis greatly improves your odds of choosing the right answer, especially if the physics part is a little bit fuzzy. This greatly increases your confidence on that exam, and it's applicable to any type of problem. Okay, so we've covered everything there is to know about dimensional analysis, and I think we're ready to take on this lesson's challenge problem. Previously, in Newton's law of gravitation, we used dimensional analysis to find the units of the gravitational force constant, but it can also be used to help derive equations as well, as we'll see in today's challenge problem. This challenge problem involves Stokes' law, which is encountered in fluid mechanics. It states when a sphere moves through a fluid, it encounters a drag force F, which is a force that opposes the direction of motion. The force's magnitude is related to the product of the radius of the sphere r, the fluid's viscosity eta, units of kilogram inverse meter second, the velocity of the sphere v, and a dimensionless constant alpha, and it's related by the formula F equals alpha times r to the I times eta to the j times v to the k. And this problem asks to determine the integer exponents I, j, and k for r, v, and eta in the expression for the drag force. Okay, lots to unpack here, and seems especially daunting asking to find 3 unknowns and only 1 equation. So let's form a general strategy before we start tackling this problem. So first, in the equation for the force's magnitude, the units must balance on both sides of the equation. And number 2, the exponents of each factor can be chosen appropriately to ensure this unit balance. So starting with the left-hand side of the equation, we have the force term, which can be decomposed into the base units of kilogram meters per second squared. And this must be equal to the units on the right-hand side. We can bracket each term and substitute each term's respective units. Beginning with alpha, we were given this is a unitless quantity, so we can move on. R has units of the meter, eta has units of the kilogram inverse meter second, and v has units of meters per second. Next, we can collect like terms and combine them together using the law of exponents. So meters m is then raised to the I minus j plus k power, kilograms kg is raised to the j power, and seconds s is raised to the negative j plus k power. Remember, each side of the equation must have the same units, so we can compare the exponent of each unit on the left-hand side with the exponent of each unit on the right-hand side. A good place to start would be with the kg kilogram, since j is the only variable in kg's exponential term. Comparing this with kg on the left-hand side, we can deduce that j equals 1. Since the seconds factor has j and only one other variable k, we can set the seconds exponential equal to -2 from the left-hand side. And this leads to a simple algebra expression having the solution of k equals 1. Finally, we can set the meters exponential equal to 1 from the left-hand side, and after substituting in our known values for j and k from above, we can solve this expression to find I equals 1. Therefore, back substituting I, j, and k into our original expression, we find the drag force is equal to linear product of alpha, r, eta, and v. And we can box this answer. This problem didn't really turn out to be that bad, and after recognizing the trick of balancing units, finding the exponentials boiled down to simple algebra problems. And this challenge problem really highlights the power of dimensional analysis. You don't have to understand Navier-Stokes equations, or pendulums, or Newton's universal law of gravitation to be able to work through and gain some familiarity with these ideas using the simple tool of dimensional analysis. It won't solve everything, and eventually you're going to need to roll up your sleeves and learn some physics, but it certainly can give you an edge and get you through some sticky situations. Thanks for watching, and I hope you enjoyed this video. Next time, I'll be diving into the world of mechanics, so stay tuned by subscribing to my channel. Make sure to hit that like button, and until next time, happy learning.